Hi class, in this part of Chapter 4 we're going to look at Newton's laws. So the last time we talked about general descriptions of motion, describing motion, position, velocity, acceleration. Now we want to talk about kind of where the motion sort of comes from. You know, how do we get accelerations, and how is acceleration related to force, and how are forces that one object pushes on another object with related to forces that the second object exerts back on the first. So we'll look at some of those things. So Isaac Newton was born in 1642, and he was thinking about laws of motion, and he was looking at other things like planets orbiting stars, the moon orbiting the earth, and things like that. And he was realizing, he made some connections. He realized that these laws that he was kind of developing about motion in his laboratory there on Earth were very similar to, or probably really exactly the same as the laws that operated in the heavens. So there were a lot of ideas way back then about why things like Jupiter and other planets went around the sun. They had interesting ideas about why these motions were occurring. Isaac Newton ended up coming up with some very simple rules that explained everything that we observed. So he came up with 3 laws of motion and then 1 law of gravity. So really 4 laws in total. And he also did a lot. He was a brilliant mathematician, and he actually developed calculus. There were 2 people actually that kind of developed calculus around the same time, Leibniz and Newton. And they did it, I believe they did it independently, but ultimately what they developed turned out to be the same thing, calculus, as we know it today. So what we're going to talk about are Newton's 3 laws of motion, and then we'll get eventually to his law of gravity as well. So Newton's first law is often called the law of inertia, and it's kind of just a written law. It doesn't really have an equation for it, but it basically says, as it's written here, an object that moves at constant velocity, or an object will move at constant velocity unless a net force acts to change its speed or direction. So by net force we mean some total unbalanced force. So what we typically do is we have an object, maybe it's a ball or something like that, and there might be a bunch of different forces acting on it. So let's imagine that it's sitting on a table here. So this object is sitting on a table, and there's different forces acting on it. There's gravity trying to pull it down. So we can represent that as a force downward, the force of gravity, like this. So I'll put the big F, G on there. Fg, big G, force of gravity. Well, that force of gravity can't be the only force acting, because if it was, then the object would fall down. So there must be another force canceling the object. So the idea is that this object is just sitting there. Assuming that it's just a ball sitting on the table, it's just sitting there. And the reason why it's sitting there is because there's no total force acting on it. There might be forces acting on it, but they all cancel out. So this force, there's another force from the table that's trying to push the ball back upward like this. And you might call that force by the table or something like that. We'll put an Ft for table. That's the force coming from the table. So there's another name for it. It's also called a normal force, and that's not really that important, but there's various names. If you took a physics class, you'd be very clear about the names of some of these forces. So anyway, we've got an object that is not changing its velocity. The velocity happens to be 0. In other words, it's not accelerating. And the reason why it's not accelerating is because there's no net force acting on it. There are forces acting on it, but they cancel out when you add them together. So forces are these arrows. They're called vectors. Just another name for something that has a certain direction and a certain size. All right, so just like velocity has direction and size, it has speed and direction. Forces have size and direction. And when you add forces together, this upward pointing force will cancel out this downward pointing force. The total net force on this ball is 0, and so it will not have any acceleration. It will maintain a constant velocity, constant speed, and constant direction. In this case, it's not traveling at all, it's not moving at all, so it's just going to sit there. In the case of this rocket ship might be out in empty space. Assume it's really far away from planets and stuff like that. If it's just moving along at a certain velocity to the right here, then it'll maintain that velocity. So if this is its velocity, it will keep that velocity. It'll keep going in that direction at a constant speed unless some unbalanced force acts on it. And that unbalanced force could be from maybe some thrust. If the engine turns on, there'll be gases that get shot out of the back of the engine. Those gases ultimately are pushing on the rocket as an unbalanced force. That would cause the rocket to accelerate. So Newton's first law is often called the law of inertia. And it says, again, just verbally, just in terms of words, it says that an object will remain at rest or will maintain a constant velocity unless acted on by an unbalanced net force, a non-zero net force. So that's Newton's first law. Newton's second law is actually an equation. And it's an equation that actually tells you what happens when you have an acceleration, or when you have a net force, I should say. So it says that the net force, the total force acting on an object, is equal to the mass of the object times the acceleration. And the acceleration is a change in velocity. But if you remember, velocity times mass is momentum. So if there's a change in velocity, meaning there's an acceleration, there could be a change in momentum. So really technically, this equation here is actually more correct. The total force acting on an object is equal to the rate of change of the momentum. It tells you that the momentum will change if there's a net force acting on the object. Now again, momentum is mass times velocity. So for momentum to change, that means that possibly the mass could change, or possibly the velocity could change, or both. Most situations that we'll encounter, the mass is staying constant. So really what's happening is that a change in momentum is really just a change in velocity, which is an acceleration. So F equals ma is Newton's second law, and that would be valid if the mass is not changing. But there are situations where the mass could change. Again, thinking about the rocket example, when a rocket is being launched or as it's flying through space, as the thrust from its engine is pushing it, providing a force, the gases are leaving the rocket. The rocket is actually losing mass. So it's actually kind of this change in momentum for the rocket is actually a combination of mass being lost as well as velocity or speed being increased. So there's a change in mass as well as a change in velocity in terms of for a rocket that's accelerating when it's losing mass because of the gases coming out the back. So that's Newton's second law. It says that force equals mass times acceleration. So as a little example, if I had a flat surface like this, and imagine I had a block on the surface like this, and that block had a certain mass, let's say 10 kilograms, 10 kg. Okay. So, and let's assume, think about this surface here, let's just assume it's a really, really slippery surface so we don't have to worry about friction, the rubbing of this block on the surface. Just let's ignore that. Let's suppose it's a really, really, really thin, or really, really smooth surface. And so there might be a force pushing the box this way. We'll call that F. F is our force. Right. So if we have a value for this, force is given, the standard units of force are called the Newton, named after Isaac Newton. So let's suppose the force is, just to do a quick little calculation, let's suppose the force is 100 newtons. 100 newtons. That's the standard unit of force, 100 newtons. And we have a mass of 10 kilograms. The way we can calculate the acceleration of that object is to take the force and divide by the mass. So the acceleration then of that object is the force, 100 newtons, divided by the mass of 10 kilograms, 10 kg. And so 100 divided by 10 is 10, so that's going to be 10. And the units would end up, whoops, that's not a very good 10. The units would end up being meters per second squared. So that would be our acceleration of that block. And again, that's assuming that this is the only force acting on the block. So that's an application of Newton's second law. Then Newton's third law, as is shown here, is a little bit more complicated. So it's a little bit more kind of difficult to think about. And it says for every force there's always an equal and opposite reaction force. Now, the word reaction isn't the best word because it kind of tends to suggest that when when some object acts on another object, that other object reacts and there might be some delay. So oftentimes when there's a reaction, there's kind of a delay. Well, there isn't a delay here. What it means is that when one object pushes on another object, the other object pushes back at the same time with the same magnitude force, the same size force. So, for example, if you pushed against a wall, so here's a wall, and there's a floor, and here you are standing here. Your arms are going to push against this wall, and your body's here, and your legs are here. So you are going to push against the wall. So this is a force. I'm going to write it as the force by you. See if I can write this here. The force by you on the wall. And the way we'll write that is just to kind of abbreviate it a little bit. We'll write this as the force by you, so we'll put a y there, on the wall. Okay, so the force by you on the wall. You are pushing on the wall in this direction to the right. You're pushing on the wall. Now, if that wall is really flimsy, it might start to tip over. Right? But suppose it's a really rigid wall. And either way, whether it does move or not, it doesn't really matter. What this Newton's third law is saying is that because you're pushing to the right on the wall is actually pushing back on you to the left. So there's a force, and technically, the force is acting on your hands because that's where you're touching the wall. But just so we don't have all these lines confused, we'll draw the line over here, the arrow over here. So there's a force acting on you, that's by the wall. So I would write force by the wall on you. So FWY. So that's the force by the wall acting on you. This is the force by you acting on the wall, YW. So notice how those subscripts are switched. So Newton's third law says that the force that you push on the wall with is equal but opposite the force that the wall pushes back on you with. Now, it's hard to, you might think, well, why don't I go flying backwards? If the wall is pushing on me back this way, why don't I go flying backwards? Well, you would if you were on ice and you had ice skates on. If you pushed on the wall and this is a perfectly frictionless surface, you had ice skates on and nice slippery ice, if you pushed on the wall, you would go flying backwards. You would go flying back out away from the wall because of that force by the wall on you. So Newton's third law talks about two pairs of forces, or a pair of forces, acting on different objects. You pushing on the wall and the wall pushing on you. This force here is acting on the wall, it's coming from you. This force here is acting on you, it's coming from the wall. All right? So that's the key to Newton's third law. For every single force, there exists an opposite, an action-reaction kind of partner force, an equal but opposite partner force. So if we think about, we'll look at a couple other examples, and I'll show you a nice little YouTube video that I found that demonstrates this, the fact that these two forces are equal in magnitude. All right? So let's just look at a couple things real quick before we get to that video. So here's a question. So how does the force the Earth exerts on you compare with the force you exert on it? All right, now there's two ways to think about it. You can think about the gravitational force. So if this is the Earth, let's say, and you're standing on the Earth, in a sense there's two different forces that the Earth is acting on you with. So that's a nice picture of you. The Earth is pulling down on you by the force of gravity. So what we often can do is we can draw a little diagram of just you all by yourself so we don't confuse all these different diagrams. So here's a force of you all by yourself. Pulling down on you, there is a gravitational force. Earth's gravity is pulling down on you. Okay? And we often call that force, it's kind of your weight. We talked about this a little bit last time. Technically, your weight is what a scale measures. But if you're just sitting still on the ground and you're standing on a scale, your weight is equal to the force of gravity. Okay, so you can measure your weight as being equal to the force of gravity, unless you're accelerating up in an elevator or something like that, as we saw in the last lecture. So the force of gravity is pulling down on you. That's one force that the Earth is exerting on you. Well, if you're standing on the surface of the Earth, there's actually another force. There's that upward force that the surface of the Earth itself is pushing on you with. All right, that's what we had called before a normal force. In this case, that's really coming from the Earth because you're standing on the Earth. But maybe you were standing on a table or something like that instead. So really it would be the table pushing up on you. All right, but there's some upward force acting on you. And maybe that's coming from the earth directly because you're touching it, you're standing on it. Or maybe that's coming from a tabletop because you're standing on the table. Whatever it is, there's some other force pushing up on you. Well, let's focus on this force of gravity. All right, Fg. Fg is often called your weight. Again, as long as you're not accelerating in an elevator shaft or something like that. And so that force has an equal but opposite partner. This is a force acting on you by the earth. It's the force that the earth is pulling down on you with. Well, there's an equal but opposite force that you are pulling up on the earth with. And so if we drew the earth all by itself, there would be a force that you are pulling up on the earth with. And that's equal but opposite to that force that the earth is pulling down on you with. We can call that Fg, little g or big G, whatever you want to use. So these two forces are equal but opposite in magnitude. Right? Another example is kind of, just to think about it, it's kind of strange. If you think about a ball falling down out of the sky, the earth is here again and the ball hasn't hit the surface yet. If we ignore air resistance, just imagine that there's no air, then there is a force downward by the earth on the ball. So we can write this as a force by the earth acting on the ball. So FEB, the force by the earth acting on the ball, pulling the ball down. And we know the ball falls, and it falls pretty fast, and it eventually might be traveling pretty fast when it actually hits the ground. Well, before it hits the ground, let's just think about the fact that there is an equal but opposite force pulling up on the earth. And we would call that FBE. We would call that the force by the ball on the earth. The earth is pulling up on the ball with the same force that the ball is pulling up on the earth with the same force that the earth is pulling down on the ball with. Those forces are the same, equal but opposite. You might say, well, how can the ball be pulling up on the earth with the same force the earth is pulling down on the ball? That doesn't seem right. Well, it is true, and it's a nice little demonstration that you'll see in this YouTube video. But it is true, and you might say then, well, why isn't the earth moving? Why isn't the earth moving up to the ball while the ball is moving down to the earth? Well, remember Newton's second law, F equals ma. F equals, if I can write it here, ma. Whoops, ma. So if I wanted to describe the acceleration of the ball, I would put in here the mass of the ball and the force acting on the ball. So I'd put this FEB in here, whatever that might be, some number, let's say 20 newtons, I don't know. And I would put the mass of the ball here. So I'd take that force and I'd divide by the mass to get the acceleration. And the mass of a ball might be 50 grams, I don't know. All right, so I'd get some acceleration. So again, what I would do is I'd divide by the mass. And that would, let me rewrite that. So let's just erase this, scratch it out. So to calculate acceleration, I would take the force on the object, divide by the mass. That would be the acceleration. All right, so the force on the ball from the earth, maybe it's 20 newtons. I'm going to divide by the mass, maybe it's a half a kilogram, something like that. So that's going to give me an acceleration of 20 divided by a half is going to be like 40 meters per second squared, something like that. So that would be the acceleration of the ball. Seems like, like a big number. Okay. Well, what about the acceleration of the earth? Well, I have the same force acting on the earth, 20 newtons. Same force acting on the earth is what's acting on the ball in magnitude, but opposite direction. And now I'm going to divide by the earth's mass. Well, the earth's mass is a huge number, 10 to the 24 kilograms. It's huge. That 20 Newton force divided by the huge, incredible mass gives you an incredibly small acceleration that you will have a really, really hard time noticing. So for all practical purposes, we just say that it's zero. The earth doesn't really accelerate as we drop a ball from the sky down to the surface. But there are these forces, equal but opposite action-reaction partners. So how does the force of the earth that the earth exerts on you compare to the force you exert on it? Hopefully now you can answer that earth and you exert equal and opposite forces on each other. So here's another question. We have a compact car, a small car, and a Mack truck, a big heavy truck. They have a head-on collision. Which of the following statements are true? So we've got the situation where a really big truck, so a little tiny car, we'll draw that first, it's going to move this way. All right, whoops, big arrow. And this big old truck is going to move this way, and they're going to collide. There's going to be some moment when they are touching. They're getting all crunched up because they're colliding. All right. So during this collision, the car is going to be pushing on the truck this way, and the truck is going to be pushing on the car to the left. They're going to be pushing on each other. So this arrow to the right is the force on the truck by the car. This force on the left is the force on the car by the truck. Those are equal but opposite partners, action-reaction partners, and they should be equal in magnitude. All right, so let's see what we can answer here. Let's see, the force of the car on the truck is equal and opposite to the force of the truck on the car. That is true. They are equal and opposite forces acting on each other. The momentum transferred from the truck to the car is equal and opposite to the momentum transferred from the car to the truck. That sounds kind of complicated. But again, the idea, remember that Newton's second law says that force is equal to the rate of change of the momentum. So if I have a certain force acting on an object, that's going to be equal to the change in momentum, the rate of change, like the amount of momentum that changes divided by time. So if these forces are equal, then the changes in momenta are equal of each one. And momentum, again, is mass times velocity, not just velocity. Okay? And then the change of velocity of the car is the same as the change in velocity of the truck. Well, that's probably not true, right? Because it's not changes in velocity that are related to forces. It's changes in momentum that are related to forces. Mass plays a role as well. So let's see what the answers are. Yes, true, true, false. So true, the force of the car on the truck is equal and opposite to the force of the truck on the car. True that the amount of momentum that the truck changes is equal to the amount of momentum, equal and opposite to the amount of momentum that the car changes by. Those changes in momentum are just related to the forces. But then false, the change in velocity of the car is not the same as the change in velocity of the truck. So let's check out that video really quick. What this video is going to show is some loops, some kind of elastic loops connected to some carts. And these carts have a certain mass to them. And one cart, they'll have several different scenarios where one cart is the same as the other one, where one cart is much more massive than the other one, where one cart is stationary and the other one's moving. When they're both moving, they'll show several different situations. But what you'll notice is that in every situation, the amount of compression of these spring-like things is the same on both carts, indicating that the forces are the same. So these spring-like things that you'll see, these spring-like bands that you'll see getting compressed, it requires a certain force to compress them a certain distance. And you'll notice that the amount of distance they're compressed is the same on either object that's colliding. And so the forces, the equal and opposite forces, are the same. So let's just watch this, and I'll point some of those things out. So each of the following 5 collisions, compare the amount each loop compresses in order to determine which cart is exerting more force. So here they go, equal ones. And watch it in slow motion. There's the compression, and the amount of compression on each one looks almost exactly the same. Those are equal carts. Now we got a really heavy cart and a light cart. And now watch it in slow motion. The amount of compression is nearly identical as far as you can tell. So the forces are equal but opposite. And then the lighter cart goes flying back much faster than the heavy one. There's an example of a heavy cart colliding with a stationary lighter cart. And see that compression of those two springy things? It's nearly identical, showing that the forces are equal but opposite. And here's the opposite one where the big heavy thing is stationary. And again, those springy things are compressed almost exactly the same. Forces are equal but opposite. And so depending on how these collisions occur, you can see that there's different responses to those equal but opposite forces. The big heavy object doesn't respond as much because it's big and heavy. The lighter object responds more because it's much lighter. So that's the little video, and this is, I'll post this link, but you can see the link up here if you can see that. I'll post that in D2L if you want to watch this again. But that's all for now. So going back really quick, what we learned is about Newton. He discovered 4 laws of motion and a law of gravity, or 3 laws of motion and a law of gravity. And he realized that these laws govern not just stuff that happens on the Earth, but stuff that happens throughout the universe, as far as he could tell. And then his 3 laws of motion are his law of inertia. Objects move at constant velocity as long as no net force is acting on them. And then there's the second law that basically says that force is mass times acceleration, or more correctly, more generally, it's the rate of change of momentum. And then the third law is for every force there's an equal but opposite force. So the next little lecture we'll look at, we'll talk about some conservation laws. We'll think about situations where certain quantities are conserved, are not changed. And that'll be a really important concept to think about when you look at planetary orbits and other things like that. So have a good night.